Friends, accuracy is the closeness with which an instrument reading approaches the true value of the quantity being measured. Precision is a measure of the reproducibility of the measurements. It is a measure of degree of agreement within a group of measurements. Precision is not the guarantee of accuracy. An instrument with more significant figure has more precision. Sensitivity, it is a ratio of magnitude of output signal to the magnitude of input signal applied to the instrument. Sensitivity equal to output by input. An instrument requires high degree of sensitivity. Sensitivity is directly proportional to 1 by deflection factor. Resolution, the smallest change in input which can be detected with certainty by an instrument is its resolution. Linearity is a behavior of instrument in which the output signal strength varies in direct proportion to input signal strength. Dead zone, it is the largest change of input for which there is no output of the instrument. Dead time, time required by instrument to begin to respond to the change in a measurand. Range and span, the difference between the maximum and minimum values of the scale is called range. The maximum value of the scale is called as span. Errors, measurement error is the difference between the measured value and true value. Error equal to measured value minus true value. Error equal to minus accuracy. Error analysis. Static error, delta A equal to AM minus AT, where AM equal to measured value of quantity or actual value, AT is true value of quantity or nominal value. Relative static error, epsilon R equal to delta A by AT. Static correction, delta C equal to AT minus AM equal to minus delta A. Static sensitivity, delta Q naught by delta QI. Delta Q naught, infinitesimal change in output. Delta Q, infinitesimal change in input. Non-linearity equal to maximum deviation of output from the idealized straight line by full scale deflection into 100. Error at desired value equal to full scale value into error at full scale by desired values. Combination of quantities with limiting errors. Sum or difference of two or more than quantities. Let x equal to plus or minus x1 plus or minus x2 plus or minus x3 plus or minus x4. Delta x by x equal to plus or minus of x1 by x. Delta x1 by x1 plus x2 by capital X. Delta x2 by x2 plus x3 by capital X. Delta x3 by x3 plus x4 by capital X. Delta x4 by x4, where plus or minus delta xi is relative increment in quantity xi, plus or minus delta capital X relative increment in capital X. Delta xi by xi, relative limiting error in quantity xi. Delta x by x, relative limiting error in x. Product or quotient of two or more than two quantities. Let x equal to x1, x2, x3, or a capital X equal to x1 by x2, x3, or capital X equal to 1 by x1, x2, x3. Delta x by x equal to plus or minus delta x1 by x1 plus delta x2 by x2 plus delta x3 by x3. Composite factors, let x equal to x1 power n into x2 power m, then delta x by x equal to plus or minus n into delta x1 by x1 plus m into delta x2 by x2. Mean deviation variance, arithmetic mean x bar equal to delta x by n equal to x1 plus x2 plus and so on xn by n, where x1, x2 and so on xn gives you readings or samples. N means number of readings. Dn equal to xn minus x bar. Algebraic sum of deviation is 0. The average deviation d bar equal to sigma modulus of d by n, modulus of d1 plus modulus of d2 plus and so on, modulus of dn by small n, modulus of dn by small n. Now standard deviation for n greater than 20, standard deviation equal to sigma equal to root over sigma d square by n equal to sigma of equal to root over d1 square plus d2 square and so on dn square by n. For n less than 20, standard deviation s equal to root over sigma d square by n minus 1. Variance for n greater than 20, v equal to sigma square equal to sigma d square by n. For n less than 20, v equal to s square equal to sigma d square by n minus 1. Normal or Gaussian curve of errors for infinite number of readings. Y equal to 1 by root 2 pi sigma square exponential of minus x square by 2 sigma square. Y equal to h by root pi, y equal to h by root pi into e power minus h square x square, where x means the magnitude of deviation from mean, y means number of readings at any deviation x, the probability of occurrence of deviation x, sigma means standard deviation. Precision index h equal to 1 by sigma root 2, probable error PE r equal to 0.4769, by h. Average deviation d bar equal to r by 0.8453 equal to 1 by pi h square. Standard deviation sigma equal to r by 0.6745 equal to 1 by h root 2. PE equal to r equal to 0.8453 d bar equal to 0.6745 sigma. For finite number of readings for n greater than 20, PE equal to r equal to 0.6745 into root over sigma modulus of d square by n. For n less than 20, PE equal to r equal to 0.6745 into root over sigma d square by n minus 1. Standard deviation of mean sigma m equal to sigma by root n. Standard deviation sigma m equal to sigma m by root 2. Variance of combination of components. Let x equal to f of x1 x2 and so on, and vx equal to sigma x by dou x1 whole square into vx1 plus dou x by dou x2 whole square into vx2 plus and so on dou x by dou xn whole square into vxn, where vx1 vx2 vxn gives you standard variance of x1 x2 and so on xn. Standard deviation of combination of components. Let x equal to f of x1 comma x2 comma and so on xn. Sigma x equal to root over dou x by dou x1 whole square into sigma x1 square plus dou x by dou x2 whole square into sigma x2 square plus dou and so on dou x by dou xn whole square into sigma xn square, where sigma xn, sigma x2 and so on sigma xn is equal to standard deviation of x1 x2 and so on xn. Probable error of combination of components. Let x equal to f of x1 comma x2 and so on xn. Rx equal to root over dou x by dou x1 whole square into rx1 square plus dou x by dou x2 whole square into rx2 square plus and so on dou x by dou xn whole square into rxn square, where rx1 rx2 and so on rxn is the probable error of x1 comma x2 comma and so on xn. Uncertainty of combination of components. Uncertainty is the deviation of measured value from unique sample of data sample in terms of degree of confidence of user. Let capital X equal to f of x1 x2 and so on xn. Wx equal to root over dou x by dou x1 whole square into wx1 square plus dou x by dou x2 whole square into wx2 square and so on dou x by dou xn whole square into wxn square, where wx1 wx2 and so on wxn uncertainties of x1 and x2 and so on xn. Order of instrument. Zero order instrument as input changes, output also changes, immediately called zero order system. Example resistor. First order system, an input changes, output also changes, but not immediately, takes some delay but with oscillations. Example heater. V0 equal to Vi into 1 power e power minus t by Rc. Second order system as input changes, output also changes with some delay and oscillations. The analog instruments are of second order, which have damping factor between 0.6 to 0.8. Standards: length meters, temperature second, temperature Kelvin, voltage volt, current ampere. Galvanometers: D arsenal galvanometer, the deflecting torque Td equal to B into I into N into A, Bina equal to Gi. B means flux density in air gap, Weber per meter square. I means current through moving coils, amperes. N means number of turns in coil. A means LD, area of coil in meter square. L comma D means length of vertical and horizontal side width of coil respectively. M. G means distance constant of galvanometer. Controlling torque Tc equal to K into theta F, where K equal to spring constant of suspension and Newton meter per radian. Theta F equal to final steady deflection of moving coil radians. Final steady deflection theta F equal to NBA by K into I, G by K into I. Dynamic behavior of galvanometers. Torques in galvanometers. Inertial torque Tj equal to J into d square theta by dt square, where theta means deflection at any time t radians. J means moment of inertia of moving system about the axis of rotation kg meter square. Damping torque Td equal to capital D into d theta by dt, where d equal damping constant. Controlling torque Tc equal to k theta, where k equal control constant. Deflecting torque Td equal to Gi. Equation of motion: Tj plus Td plus Tc equal to Td, J into d square theta by dt square plus d into d theta by dt plus k theta equal Gi. If capital D square less than 4 kJ, galvanometer is underdamped. If capital D square equal 4 kJ, galvanometer is critically damped. If capital D square is greater than 4 kJ, galvanometer is overdamped. total resistance of galvanometer circuit for critical damping R equal to G square by 2 root kj. External series resistance required for critical damping Re equal to R minus Rg equal to G square by 2 root kj equal to minus Rg, where Rg is resistance of galvanometer. Sensitivity, current sensitivity SI equal to theta F by I equal to G by K radians per amperes. SI equal to D by I into 10 power 6 scale divisions per microamperes. SI equal to 2000 G by K in 10 power 6 millimeter per microamperes. Voltage sensitivity SV equal to D by IRG into 10 power 6 scale division per microvolt. Mega ohm sensitivity S naught equal to D by I in 10 power minus 6 mega ohms per scale division. Remember, sensitive galvanometer is one which produces a large deflection for a small current. Analog meters, classification of analog meters, representation, indication, deflection of pointer, voltmeter, ammeter, wattmeter. Recording లో అయితే పొటెన్షియోమీటర్, galvanometer, పొటెన్షియోమీటర్ రికార్డర్, galvanometer రికార్డర్, XY ప్లాటర్. ఇంటిగ్రేటింగ్ ఇన్స్ట్రుమెంట్ అయితే అందులో ఎనర్జీ మీటర్, స్పీడోమీటర్. నల్ డిటెక్టర్ అయితే పొటెన్షియోమీటర్. Mechanism and principle: electromagnetic effect, electrostatic effect, heating effect, induction effect, Hall effect. Torque in analog meter, deflecting torque TD. Deflecting torque is proportional to quantity under measurement. The torque deflects the pointer away from initial or zero position. TD is directly proportional to measurable quantity. Controlling torque TC. The controlling torque is opposite to deflecting torque. When deflecting torque equals to controlling torque, pointer comes to final steady state position. At equilibrium, TC equal TD. Control torque is also used to bring the pointer in zero initial position if there is no deflecting torque, except in PMMC. In all other instruments, if the controlling spring is broken, then the pointer moves to the maximum position of scale. Controlling torque is powered by spring control and gravity control. Damping torque, it is used to damp out oscillations at final steady state position. The time response of the instrument depends on damping torque. Damping torque is powered by air friction damping, used where low magnetic fields are produced. Fluid friction damping, used where deflecting torque is minimum. Eddy current damping, used where permanent magnet produces the required deflecting torque. Error in analog meters, frictional error. To reduce the frictional error, the torque to weight ratio of the instrument should be high. Temperature error, due to change in temperature, change in resistance of meters and shunts and series multipliers occurs. To reduce this effect, resistance are made up of manganese material. Frequency error, due to change in frequency, error is produced in instrument because change in frequency causes change in reactance. To reduce this error, a capacitance is used in case of voltmeter, and for ammeter, time constant and shunt impedances are maintained at same value. Permanent magnet moving coil, PMMC, low control spring, permanent magnet core, moving coil, pointer, soft steel iron, upper control spring. Deflecting torque TD N equal to NBAI. TD equal to GI, N equal to number of turns, B means flux density, A means area of core, I means current to be measured. Final steady state deflection theta equal to capital G by capital K into I, where K is spring constant. PMMC instrument measures only DC or average values. Scale is linear. Spring is used for controlling torque. Damping torque provided by eddy current damping. It has more torque to weight ratio, so accuracy and sensitivity is higher compared to other instruments. In direct measurements, the PMMC measures up to a current of 50 milliamperes or a voltage of 100 millivolts without any external device. Enhancement of scales of ammeters and voltmeters. Ammeter shunts, RSH, RM, basic meter, IS, RSH, RSH equal to IM into RM equal to IM into RM. I equal to 1 plus RM by RSH into IM. I means current to be measured. IM equal to IFS, full scale deflection current, amperes. RM means internal resistance of meter, ohms. RSH means resistance of the shunt, ohms. Shunt resistance RSH equal to RM by M minus 1, where M equal to I by IM, that equal to 1 plus RM by RSH. M means multiplying factor for shunt. To reduce the temperature effect, swamp resistance made up of manganese is added in series with ammeter. Remember, universal R, right and shunt 1 2 3 current draw చేస్తుంది. Universal shunt R1 R2 R3 IM RM meter. For switch at a position 1, R1 equal to RM by M minus 1, for switch at position to R2 equal to R1 plus R2 by R1 plus M by R1 plus Rm by M2 for switch at position to R2 equal to R1 plus Rm by M2 for switch at a position 3 R3 equal to R1 plus Rm by M3 where M1 equal to I1 by M1 IM M2 equal to I2 by IM M3 equal to I3 by IM. Voltmeter multipliers. Multiplying factor for multiplier M equal to V by V equal to 1 plus RS by Rm. Resistance of multiplier RS equal to M minus 1 into Rm. RS means multiplier resistance, Rm means internal resistance of meter. Potential divider arrangement. R1 equal to M1 minus 1 into Rm. M1 equal to V1 by V. R2 equal to M2 minus M1 into Rm. M2 equal to V2 by V. R1 means resistance between point A and B. R2 means resistance between point B and C. R3 means resistance between point C and D. R4 means resistance between point D and E. Voltmeter sensitivity. The smallest value of input that the instrument can sense. SV equal to 1 by IFS equal to RS plus Rm by V ohms per volt, where IFS equal to full scale current. To reduce loading effect, a voltmeter with a higher value of sensitivity is preferred. Moving iron instruments. The moving iron instruments are based on the principle of magnetic effect of electric current. Deflecting torque TD equal to half I square dl by d theta. Deflection theta equal to half I square by k into dl by d theta. For linear scale, theta into dl by d theta equal constant. Scale is cramped at lower and higher end, where L means inductance of moving iron instrument. Moving iron instrument measured both AC and DC quantities. In case of AC, it measures RMS value. Scale is non-linear. Controlling torque is provided by spring and air friction damping is used. Curve between dl by d theta and theta is rectangular hyperbola. Shunts for moving iron instruments. ISH by IM equal to R by RSH into root over 1 plus omega L by R whole square by root over 1 plus omega LSH plus by RSH whole square. For the instrument to measure true value at all frequencies, LSH by RSH equal to L by R. Multipliers for moving iron instruments. Voltage multiplication factor M equal to V by V, that equal to root over R plus RS whole square plus omega square L square by root over R square plus omega square L square. Errors in moving iron instrument. Shunt capacitor LR coil, series resistance, shunt capacitance C equal to 0.41 into L by RS square. Eddy currents when omega is small, IE dash equal to omega square MLEI by RE square, where omega is large, IE dash equal to MI by LE equal constant, where RE, LE resistance and inductance of eddy current path. Moving iron instrument is not suitable for measurement of current or voltage for frequency above 125 Hz because eddy current is constant at higher frequency. The voltmeter is made independent of input supply frequency by connecting a capacitor in parallel to the series multiplier resistance RS to reduce hysteresis error. The iron part of moving iron is made up of nickel iron alloy. To reduce the external stray magnetic field, the instrument is kept inside the iron case or iron shielding is done. Electrodynamometer. If I1 and I2 are DC current, that is I1 equal to I2 equal to I, then TD equal to I square dm by d theta. Measure average value. If I1 and I2 are AC current and no phase shift, I1 equal to I2 equal to I, then TD equal to I square dm by d theta. Measure RMS value. If I equal to Im1 sin omega t and I2 equal to Im2 sin omega t minus phi, then TD equal to I1 I2 cos phi dm by d theta. It measures RMS value, where I1 equal to Im1 by root 2 and I2 equal to Im2 by root 2. Electrodynamometer instrument is a transfer instrument. It measures both AC and DC. Scale is non-linear. Its sensitivity is lesser than PMMC and moving iron type instruments. Its sensitivity is lesser than PMMC and moving iron type instruments. Ratio meter. Deflecting torque acting on coil 1, TD1 equal to N1 BL1 D1 I1 cos theta. Deflecting torque acting on coil 2, TD2 equal to N2 BL2 D2 I2 cos theta, where I1 I2 current in coil 1 and 2, N1 N2 number of turns in coil 1 and 2, L1 L2 length of coil 1 and 2, D1 D2 width of coil 1 and 2, V means flux density of magnetic field. Deflection at equilibrium, theta equal to K times that of I1 by I2. Measurement of power and wattmeters. Measurement of power, DC circuits, ammeter connected between load and voltmeter. Power consumed by load, P equal to VI minus I square RA. V means voltage across voltmeter, I means current through ammeter, RA means resistance of ammeter, percentage error in reading, I square RA by VI into 100. Voltmeter connected between load and ammeter. Power consumed by load, P equal to VI minus V square by RV, where V means voltage across voltmeter, I means current through ammeter, RV means resistance of voltmeter. Percentage error in reading, V square by RV into VI into 100. AC circuits. Instantaneous power, P equal to VI equal to Vm Im sin omega t into sin omega t minus phi, where V equal to Vm sin omega t, I equal to Im sin omega t minus phi. Average power, P equal to Vi cos phi equal to Vm Im by 2 into cos phi, where V, I equal to RMS value of voltage and current, cos phi equal to power factor of the load. Let V equal to V0 plus sigma n equal to 1 to m Vn sin n omega t plus theta n, and I equal to I0 plus sigma n equal to 1 to m In sin n omega t plus phi n. Then P average equal to V0 I0 plus half into sigma n equal to 1 to m Vn In cos of theta n minus phi n. Wattmeter reads average active power. Electrodynamometer, wattmeter. Instantaneous torque, Ti equal to I1 I2 into dm by d theta, where I1 I2 means instantaneous values of current in pressure and current coils, M means mutual inductance. Deflecting torque, Td equal to Vi by Rp into cos phi into dm by d theta. Rp means resistance of pressure coil. Controlling torque, Tc equal to k theta, where k means spring constant, theta means final steady of deflection. Deflection theta equal to k1 and dm by d theta into P, where P means power being measured Vi cos phi. K1 means K1 tends to 1 by Rpk. Scale is linear in terms of power as theta tends to is directly proportional to P. Errors in electrodynamometers, wattmeters. Correction factor K. The correction factor is a factor by which the actual wattmeter reading is multiplied to get the true power. For lagging power factor, K equal to cos phi by cos beta cos phi minus beta. For leading power factor, K equal to cos phi by cos beta cos phi plus beta, where phi means angle between current and the current coil and voltage of pressure coil. Beta means angle between current and voltage of pressure coil. True power equal to correction factor into actual wattmeter reading. For very small beta, actual wattmeter reading equal to true power into 1 plus tan phi tan beta. Error equal to tan phi tan beta into true power equal to Vi sin phi tan beta. Percentage error equal to tan phi tan beta into 100. True power equal to Vi cos phi, where V means voltage applied to pressure coil, I means current in current coil. Power in polyphase systems. Blondel's theorem. If a network is supplied through n conductors, the total power is measured by summing the readings of n wattmeters. So arrange that a current element of a wattmeter is in each line and the corresponding voltage element is connected between that line and a common point. And if the common point is located on one of the lines, then the power may be measured by n minus 1 wattmeters. By n minus 1 wattmeters. 2 wattmeter method. Reading of P1 wattmeter, P1 equal to root 3 Vi cos 30 degrees minus phi. Reading of P2 wattmeter, P2 equal to root 3 Vi cos 30 degrees plus phi. Total power consumed by load, P equal to P1 plus P2. Power factor cos phi equal to cos of tan inverse of root 3 P1 minus P2 by P1 plus P2. Tan phi equal to root 3 into P1 minus P2 by P1 plus P2. V means phase voltage, I means phase current, phi means angle between phase current and phase voltage. Reading of wattmeter, different power factor. 1. Phi equal to 0, cos phi 1, P1 root 3 by 2 VL IL, P2 root 3 by 2 VL IL, P equal to P1 plus P2 root 3 VL IL, comment P1 equal P2 equal reading. When serial number 2, phi equal 30 degrees, cos phi 0.866, P1 VL IL, P2 VL IL by 2, P equal to 1.5 VL IL, comment P1 equal to P2. When phi equal to 60 degrees, cos phi equal 0.5, P1 is root 3 by 2 VL IL, P2 is 0, root 3 by 2 VL IL, comment P2 equal to 0, P2 equal to P. When cos phi equal to 0 plus V1 VL IL by 2, P2 V minus VL IL by 2, P equal to 0, comment P1 equal to minus P2. When wattmeter readings comes into negative, reverse either PC or CC terminal and that take the reading of negative wattmeter. Measurement of energy. Energy meter is an integrating instrument which adds the energy cumulatively over a period of time. Energy equal to power into time. Energy equal to integration of 0 to t, P into dt, kilowatt hour. Energy meter works on principle of induction motor. The meter which measures AC energy is called watt hour meter. The meter which measures DC energy is called amp hour meter. Deflection torque TD is directly proportional to braking torque TB is directly proportional to N, where N is speed of discs in RPS. At balance, TD equal to TB, integration of P dt equal to K into integration of N dt. Energy is directly proportional to N dt. Energy meter constant EMC equal to number of revolutions made by disc by energy recorded in kilowatt hour. K equal to N by P into T. P means power in kilowatt hour, T means time in hours. Percentage creeping error equal to revolution of errors due to creeping per hour, revolution of disk due to total load per hour into 100. Potential coil of energy meter should be highly inductive so that it measures the true energy. Compensation in energy meter. Lag compensation through lag coil or shading coil. Low load or friction adjustment by using shading loop. Over friction or creeping by providing holes or slots on rotating disc. Overload compensation by keeping saturable shunt magnets in series magnet or current coil. Over voltage compensation by keeping saturable shunt magnet in shunt magnet. Temperature compensation by making permanent magnet of material. Speed adjustment by adjusting position of brake magnet. Creeping error is always positive if either potential coil or current coil is wrongly connected, then the disc rotates in the opposite direction. Measurement of resistance. Low resistance, all resistance of order of 1 ohms and below. Example, winding coils of electrical motors, generators and transformers. Medium resistance from 1 ohm upwards to about 0.1 mega ohms. Examples, resistance of phases, potentiometers. High resistance, all resistance of the orders of 0.1 mega ohms and above. Example, insulation of electrical cable and windings, insulation of motors, generators and transformers. Measurement of medium resistance. The different methods employed are ammeter, voltmeter method, Wheatstone bridge method, ohm meter method, substitution method. Ammeter, voltmeter method. RM equal to voltmeter reading by ammeter reading equal to V by I. RM means measured value of resistance. Circuit for higher resistance. True value of resistance R equal to RM1 minus RA. RM equal to RM1 into 1 minus RA by RM1. 1 minus of RA by RM1. RM1 is measured value of resistance. RA means resistance of ammeter. Relative error epsilon R equal to RM1 minus R whole by R equal to RA by R. To get minimum error, the test resistance should be more than the ammeter resistance so that this adjustment is suitable for measurement of high resistance. Circuit for lower resistance. True value of resistance R equal to RM2 into RV by RV minus RM2. RM2 means measured value of resistance. RV means resistance of voltmeter. For RV far greater than RM2, R equal to RM2 into 1 plus half RM2 by RV. Relative error epsilon R equal to RM2 minus R by R equal to minus R square M2 by RVR. For RV far greater than RM2, approximation relative error epsilon equal to minus R by RV for RM2 is nearly equal to R. This circuit is suitable for measurement of low resistance under medium scale range to get minimum error. Relative errors for above two cases are equal when true value of resistance R equal to root A RA into RV. Wheatstone bridge. At balance, R equal to S into P by Q. PQRS. S is the variable resistance. Sensitivity of R equal to capital S into whole by P by Q. PS by Q అనుకోవచ్చు. The sensitivity of Wheatstone bridge SB equal to theta whole by delta R by R, that equal to SV ESR whole by R plus S whole square. SB equal to SV into E whole by P by Q plus 2 plus Q by P, where SV means voltage sensitivity of galvanometer millimeters per volt. E means bridge voltage. P comma Q means branch resistance. Theta means deflection of galvanometer millimeter. For bridge with equal arms, SB equal to SV into E by 4. For maximum bridge sensitivity, P by Q equal to R by S equal to 1. Sensitivity of bridge is most important parameter as compared to accuracy, precision and resolution. Equivalent circuit of Wheatstone bridge. R plus delta R P S Q R naught into D R naught D. Galvanometer current IG equal to E naught by R naught plus G. E naught means Thevenin's or open circuit voltage appearing between terminals B and D with galvanometer circuit open circuited. G means resistance of the galvanometer circuit. E naught equal to E into R plus delta R by 2 R plus delta R minus half. E that equal to E of delta R by 4R. Yes, delta R is far less than R. Delta R change in resistance R Thevenin's equivalent resistance of bridge R naught equal to Rs by R plus S plus PQ by P plus Q. Galvanometer deflection theta equal to SV ES delta R by R plus S whole square, that equal to SI ES delta R by R naught plus G into R plus S whole square, where SI means current sensitivity of galvanometer, bridge sensitivity SB equal to theta whole by delta R by R, that equal to SI ESR by R naught plus G into R plus S whole square. Current sensitivity SI equal to theta by Ig millimeter by mu amps, where theta means deflection in galvanometer, Ig means current in galvanometer. Voltage sensitivity SV equal to theta by VTH millimeter per volt, where VTH means voltage across galvanometer. In Wheatstone bridge method, the effect of lead resistance is not eliminated, hence it is not suitable for measurement of low resistance. Hence it is not suitable for measurement of low resistance.